Exponential growth problem. The general exponential growth equation can be expressed in the following way. Q of t equals q sub 0 e kt. Now to define these terms, q sub 0 is the original amount, k is the growth constant, t is the time, and q of t is the final amount. So now let's apply this exponential growth equation to a real-life problem. Problem. In a biology experiment, a researcher is growing bacteria in a petri dish. She starts with 2,000 bacteria, and after 3 hours she has 5,000 bacteria. If conditions do not change, how much bacteria can she expect to have after an additional 2 hours? Under ideal conditions, bacteria grows exponentially. So to solve this, let's first draw a picture that we can label and put all of our given data on it. So we have our 3 petri dishes. There's 2,000 in the first one, and then 3 hours later there's 5,000, and then 2 hours after that we don't know, so we'll call it X. So now we've got all of our data displayed, so we can just now plug in the data into our exponential growth equation and find what we need. So step 1, find the k. So to find the k, we only want one unknown in that equation. So we're going to use the final amount is 5,000, the initial amount is 2,000, and the time will be 3 hours. Think about that a minute. We're going to go from 2,000 to 5,000 because then we know the initial amount and we know the final amount. So we plug all those numbers in, and the time would be 3 hours between the 2,000 and the 5,000. And so now we have to solve this exponential equation. So first we'll divide by 2,000, and we'll get 2.5 equals e to the 3k. So now we have an exponential equation where we got to get the 3k out of the exponent. So we'll take ln of both sides. ln of 2.5 equals ln of e to the 3k, but ln and e are inverse functions of each other. So we'll get ln of 2.5 is equal to 3k. Then we need to divide both sides by 3. And k equals 0.30543. So you have to decide where to round it off, but that looks pretty nice. I guess I wouldn't round it off any less than the thousandth place, because we're going to need to use this. So k equals 0.30543. So now we need to find the x. So we'll go back and start over again with the exponential growth equation in step 2, find x. So now we'll reuse that same equation. But now the final amount will be x, and the initial amount could be either 2,000 or 5,000. You could use either one, but then you got to adjust the time accordingly. We're just going to use 5,000. So x equals 5,000 times e, and there's our growth constant, 0.30543, and then the time going from 5,000 to x is 2, so we're going to put in a 2. Now this isn't any equation just to evaluate what x is. We already have x by itself on one side. So put this in your calculator and we get approximately 9,210, and we'll round that off at least to 9,200. And I think you could definitely argue you should round it off to 9,000 because of the number of significant digits that were given in the original problem. But I like 9,200. And so that's the amount of bacteria at the final amount, 5 hours after the beginning, or 2 hours after there was 5,000 in there. It is important to note that the actual accuracy of your answer depends on the accuracy of the numbers you put into the formula, and not to the number of places your calculator gives you for an answer. So it's pretty normal that people see something on the calculator and they say, oh, all those places, that's more accurate. Not really. The calculator isn't thinking about anything, it's just terminating after a given number of decimal places. So what you have to do in a real-life experiment like this is decide how accurate was the original data, and then how are the operations that we're going to do affect the accuracy of the final outcome. So that's why I say probably 9,000 is about as good as you're going to get here. But if you're in a real life situation, that would be decisions you'd have to make.